首先那个就是档案已经开好了，就这个。
Hello everyone. Let's see something about final project presentation next week. This is our previous schedule. For next week, we have 10 minutes for each team to present your final project. So you have 6 minutes for PowerPoint presentation, and be sure to present by English. Okay. And then you need to remember to upload your PowerPoint slide 1 day before the presentation. That will take partial of your scores. Okay, and then you have 4 minutes for system and project demo. So you can run your project by your own laptop. Otherwise, you can also have the video recording how you, for example, execute your project and what are those results. Okay, that's for presentation. And your presentation slide should include the introduction to your topic and to your problem description and what kind of applications and what is the scope of your application. And most importantly, the project framework to indicate which part you use current model or modules. I believe you can download or find a lot of reference code online. It's okay, but you need to indicate which part is developed by yourself and which part you are using current modules. Okay, and then you need to emphasize the major contributions of your project. For example, what is your novelty? Or you spend a lot of time for system integration, or you can emphasize this is a very large system framework, so it takes a lot of time to develop this final project. So, and your final score of final projects will based on the problem setting and major contribution of this final project. And the last part is teamwork. So you can set up different working items and then the ratio of each members, which one is responsible for which working item. And then maybe you can give the ratio. First students took, for example, 20%, and the second person took 40%, something like that. Okay, that's all for final project presentation next week. Let's see if you have any questions. Okay, have you finished your final project? Not yet? Okay, so I need to emphasize something. For next week, if you have only PowerPoint presentation but no system demo, then the final final project will assume to be not finished or not started yet. So you will get 0 scores. Okay, so because this is very important to accomplish, complete your final project. So at least you need to demo something. Even it is incomplete project is okay, but at least you can show something, but not just PowerPoint slide. Okay, is that clear? Okay. Okay, next. Remember what we are talking about last week is about pitch shifting. So I would like to demo the results for even wave or MP3. We can shift the pitch by different settings. Okay, so let me run this program for you. Okay, so this is the original soundtrack provided by one of our classmates. And this is the original key. Okay, but for this soundtrack, I think it's not fair to estimate the frequency components because you can see she is singing with the guitar. So the frequency component analysis or frequency view will not be that accurate. Okay, next let's see what happened when we shift 4 steps down. Okay, it sounds like a little bit male voices, right? Okay, so let's jump to next example. So I should shift back to the original key.
才敢说成你。
Okay, so you can see the simple code
还
of
有多
pitch
远
shift.
才能进入你的心？还有多久才能和你接近？咫尺远近却无法靠近的那个人，也等着和你相遇。环游的星星，怎么可以拥有你？
Okay, I think this is a very beautiful song. Do you know which song it is? No? Never heard it before. Okay. So let's look a little bit about the simple code of page shift. Okay. So this is a MATLAB program. You can download the MATLAB from CCU website because it's the older software, and you can use it free within CCU campus. Okay, so the first one is audio read. Okay, so just input the name of the soundtrack, for example, song B.mp3, and then we just call the pitch shift module to indicate the original soundtracks. For example, after audio read, then we read all files content into the variable y. So we have the variable y here, and then we set the sampling rate, and then the step. The last component is step. So we can say, for example, +1, +2, or -3, -4. Okay, and then after we shift the pitch, then we get a new output soundtrack variable YY. And then we can call audio play to play YY, and then using the sampling rate fs because we have this variable when we read the original soundtrack. So we just use the original fs here. And then once we have some players, then we call the function play to play the player. Then we can play the song. Okay, so for this song, let me raise the pitch by 4 steps. Okay, so here I set the step to 4.
这深远的光景，最亲密的距离，沿着你皮肤纹理，走过曲折手臂，做个梦给你，做个梦给你。等到看你颜色满尽，等到分不清季节更替，才敢说成你。还要多远才能进入你的心？还有多久才能和你接近？咫尺远近却无法靠近的那个人，也等着和你相遇。环游的星星，怎么可以拥有你？
Okay, so by these two demos, you can see when you go to KTV to adjust the key, once we have some maybe chorus in the background. For example, once you change the shift, once you shift the key, then maybe the female voice sounds like male voice, and male voice once you shift the key, it could be even higher or lower. So you will see very similar phenomena like this. Okay, so I will ask TA to release this code for you. Then you can try by yourself how to adjust the key and how it sounds like. Maybe you can trace the component of pitch shift by yourself to see how it apply the steps or the algorithms or structures when we introduced pitch shift last week. Okay. Today, I'm going to introduce a new unit in digital video. So let's see. Currently, we have images, we have audios, and next category of multimedia will be digital video. Okay, so let's see what is video, film, or television. And film and videos are both rest on some phenomena of human perception, which is called persistence of vision. Because when we are watching movies or videos, actually they are keyframes and single frame by frame, but we play these frames in a sequence. And we use the phenomenon of human perception, persistence of vision, because when the time is very short between each frames, then our human vision tend to continuously see things happen one by one. Okay, so we can also call this phenomenon flicker fusion because they are single frames, but our brains or our vision system can fuse single frames, the previous one and next one, to a continuous animation. So that's one special abilities for human vision system. Okay, so a very important component or attribute to make persistence of vision happens is the frame rate. Because we are talking about this very special human vision abilities. Once two single frames happen within a very short time, so we use frame rate to control the times. For example, we can play single frames, 30 frames per second. Okay, so within 1 second, we can continuously display 30 different single frames. Okay, and then this helps us to create the persistence of vision or flicker fusion. But once we have too large gap between each frames, for example, one frames 5 seconds, okay, then you will see first frame and it will be static. And then after 5 seconds, you can see the next frame. So we won't have the effects of flicker fusion. Okay, so how to make animation or how to make the movie. So frame rate is very important. And usually for the applications, sometimes we call that real-time applications. If you have, for example, apply convolutional filters to all these original image frames, and you want to create different effects. But for real-time applications, we usually talk about 30 frames per second. Once you can accomplish all your processing, for example, convolution, and then you can display 30 frames per second, then we call that real-time applications. So to make flicker fusion happens, at least you need to 20 frames per second. Okay, so it can still perceived by the human vision system as a movie. But if the frame rate goes lower and lower, then you will see an individual or single frames by frames. There is no animation effects. Okay, so frame rate is a very important properties for movies or videos. Okay, next one is a sprocket pulse. Okay, we also call that perforations. That's a pulse on the side of the film used to pull film through the projector. So actually we're talking about this pulse. Okay, so you can see this is one film, and we have 4 pulses on the side of this film. Okay, so sometimes we call this film 4-perf 35 millimeter film. Okay, so next time you see 4-perf. So perf means perforations, and perforation also means sprocket pulse. So if you see this term, you can see by the film we have 4 pulses beside one film. And 35 millimeter means the width of the film. Okay, so next we will see more different format of the film other than 35 millimeter. Okay, so for standard film, aspect ratio is a very important fact. Okay, aspect ratio is the ratio of the width to the height of a film. We usually express as width to height. Okay, so once we have the difference, then you can use the width to divide it by the height, and then you can get a ratio. So this ratio is what we call aspect ratio. Okay, so for IMAX, usually they are shot on 70 millimeter films, and the aspect ratio is usually 1.44 to 1. Okay, so you can see the aspect ratio for IMAX movie is different from the traditional movies. Okay, next let's see, how do we get 1.44 to 1? Okay, so maybe we can examine the width and height of IMAX film. Because for IMAX film, the width and height is 70 millimeter to 48.5 millimeters. And if you use these two numbers, if you use 50 divided by 48.5, then you will get 1.44 something. Okay, so that's the aspect ratio of IMAX movies. Okay, so you can see actually the film is very small, but when you go to the staircase, we can see we have the projector to project the film to a very large screens. Okay, so if we can stretch aspect ratio to, for example, 28.8 meters times 19.54 meters, then we can see the complete region of IMAX film. Okay, but the sad thing is, actually when you go to different theaters, you can see different aspect ratio of the screens. Especially you pay the same money to see IMAX movies, but you will see totally different stories. Because if you go to Hsinchu, then it's IMAX, the width is only 70 something. 70. Okay. So it's not 28.8. So the screen is very small, even if it is IMAX movies. However, if you go to 大直北地环影城, okay, so you can see a real big screens. Okay, the size is 28.8, and you can see the height is 21.16 meters. Okay. So by comparing the aspect ratio, you can see how to make your money to have higher CP values. Okay, if you go to this business, maybe your money is worth it. But if you go to services with smaller screens, you pay more money. Okay, so I believe like 5 years ago, the first largest IMAX theaters, the ranking one is Daozi IMAX. Okay, so if you really go to this theater, you can see it's really large because it's about high floors. Okay, so when you're standing in front of the screen, you can tell the difference how large the screen is. And the smallest IMAX actually is in Kaohsiung. So once you go to these theaters, you can tell the difference between other IMAX theaters. Okay, and then the aspect ratio, we know the film of IMAX is 1.44 to 1. Okay, so but if the aspect ratio of the screen does not fit this aspect ratio, then you may be missing something in the original film. For example, once we have the digital IMAX, the aspect ratio is 1.38 to 1. It's indicated by this red rectangle, or other ratios by this yellow rectangles. So you can see originally we can see the complete content of this film. But once we project to different aspect ratio of different screens, then some region of the film may be cut. Okay, you cannot see that part anymore by wrong aspect ratios. Okay, so currently we are talking about some important attribute of videos. Okay, next let's see the standard of television. Okay, so the first one is standard definition television. Okay, so I'm not sure if you have noticed when you turn on your TV at home, it will appear the standard on the, for example, top right corners. You may see something like 1000 ATI or 1080p or something, 720p. Okay. Actually, it reflects the different television standards. For example, if you see 1000 ATI, that means the television is actually the resolution is 1920 times 1080. And I means it display is in internet scanning mode. And P means progressive scaling mode. We will introduce these two display mode later. Okay, so this is the resolution when we have 720p, and then it will be very different when we have the resolution 1080 videos. So we call this standard definition and high definition videos. Okay, and then we can also have different aspect ratios. For example, for wide screens, the aspect ratio is usually 16 to 9. And for conventional standards, it's usually 4 to 3. Okay, next let's see some digital television standards. Okay, so previously we have ATSC, we have DVB and ISDB. So we may quickly review the standard or what are the difference for these three standards. The first thing is it applies to different regions. For example, United States, they usually apply ATSC. In Europe, they usually use DVB, and Japan use ISDB. And when we compare the standard, we can see they have different video compression, audio compression, and transmission type. And even though they use different bit rate. Okay, so for Taiwan, actually we use ATSC just like the United States. Okay, so we have the full name for DVB and ISDB here for your reference. Okay, that's for television. Let's go back to video standards. Actually, we have different video standards for different regions. For example, NTSC is the standard in North America, Japan, Taiwan, and we also have PAL for United Kingdom and Germany, and SECAM. Okay, so why we have so many different video standards, and what problem it caused? Because previously, when we shoot videos, we use handheld devices, and the video will be recorded by the tape. Okay, so once the standard is different, then you need to transform the video content by different standards. So it's very difficult or very troublesome when we have different standards. But when we go to digital videos, so everything is solved. Okay, next let's see some terms about videos and films. The first term is frames. Okay, so now we have the name for each keyframes. Okay, because we are talking about video is a sequence of images. Okay, when we display in a very high frame rate, then we create the effects of animation. So we call this single images as frames. Okay. And then the video is displayed by a process which is called raster scanning. Okay, so let's see what is raster scanning. Okay, to display the video content, we need to scan the content of the keyframes from left to right and from top to bottom. Okay, so it's just like the ZZ scan orders when we talk about how to transform 2D images. So we have the ZZ scan orders in JPEG compression, if you remember. Okay. So let's see two more terms. When scan has finished one line and it's moved back to the left and start another, then we call this horizontal retrace. Okay. So when you move from left to right, okay, and then in the end of the right hand side, the scanning needs to go back to the left. Okay. And then you can scan the next line. So we call this horizontal retrace. Okay, and we also have vertical retrace when the scan from the bottom of the monitor to top again, we call this vertical retrace. Once we reach to the next positions of these videos or frames, then we need to go back to the previous position. So we call this vertical retrace. Okay, so you can see actually how to display the video content. We just apply vertical retrace and horizontal retrace. Then we can display all pixels of the video. Okay, so the scanning, raster scanning, we have two different methods. The first one is called interlace. The second one is progressive scanning. So interlace scanning, actually we divide the frames to two fields. The first field is odd number lines. The second field is even number lines. Okay, so we call this field upper field and lower field. So you don't have to remember this because it's very easy to remember. Because once we have the video frames and we have the line, for example, 1, 2, 3, 4, 5, okay, and then we group all odd numbers. So here we have 1, 3, 5, and then we have another field, 2, 4, 6. Okay, so one goes from before 2, so we call this field upper field, and this field is lower field. Okay, so once we partition the frames into two fields, then actually we can calculate the field rate. Okay, so field rate is just once we have 50 field per second, actually it's 25 frames per second because we know 2 field equals 1 frame. Okay, once you know the definition, the calculation will be very easy. Okay, based on the definition of upper and lower field, then we can see what is progressive scaling. So actually, we just ignore the definition of field. We just scan the line by line from top to bottom. Then we call that progressive scanning. So no special mechanism, just scan the line one by one from top to bottom. Then we call this progressive scanning. Okay, and then we can see for interlace scanning, a lower field display first one line at a time from top to bottom. Once lower field is displayed, and then we switch to upper field to display one line at a time from top to bottom. So we call this interlace scanning. Okay, so you can see once we can partition the frames into upper field and lower field, then we don't have to follow the original order of the line, 1, 2, 3, 4, 5. We can display 2, 4, 6, 8 first. And then we display 1, 3, 5, and so on. Okay, so actually, human vision system can detect such different modes. For example, for progressive scanning, usually we can see a complete display results. But for interlace, usually we can see the effects of the strips. Okay, next time when you see the effects like this, you will know it's displayed by interlace scanning. All right, so once we know the definition of interlace and progressive scanning, then we can go back to the standard. Okay, so once we have 1000 API, that means we have the resolution like this using interlace scanning because we have an I here. Once it's P, then we know it's progressive scanning. So I hope you can go back home to turn on your TV to see what is your TV goes to I or P mode. Okay. All right. Next, we jump to the multimedia technology, how to adjust the aspect ratio, because we know the aspect ratio is very important for display. Once we have a different resolution of the film and different aspect ratio of the display screen, then we need to change the aspect ratio to fit the original films to the screen. Otherwise, we will have something cut. For example, our previous red rectangle and yellow rectangles. Once the aspect ratio does not fit, then the content will be cut. Okay, so the simplest method, if we want to display the aspect ratio 4 to 3 to the screen of 16 to 9, actually we can apply letterbox. Okay, so another is called pillar box. Okay, so you can see this is a wide, pretty wide, right? Because its aspect ratio is 16 to 9. Once we need to display the screen with the aspect ratio 4 to 3, okay, so actually we can include the black parts here. Once you can compensate the original film by these black regions, then we can make a spread ratio from 16 to 9 to 4 to 3. Okay, so we call this vector box. On the contrary, if we have the original aspect ratio 4 to 3, then we can apply pillar box. Actually, we include the black regions in the left-hand side and right-hand side to make it even wider range. So the aspect ratio will be 16 to 9. Okay, I believe you have downloaded a lot of movies or videos online, and then you may see something like this, right? Have you seen the video like this? Okay, so next time you will know, actually it's just to change the aspect ratio of the original film. Then we can apply letterbox and pillar box. Okay, so you may think this method is too stupid, right? Just include the black regions. So next time I would like to introduce a new method, a very novel or smart method, which is called scene carving. Okay, so it's a way to change aspect ratio. For example, this is the original images, and we have the aspect ratio. Once we need to change to the width, just half of the original width, then you can see we remain height the same, but we change the width just half of the original width. Okay, so one way is to discover the scene, and we remove the scene. Then we can change the aspect ratio. Okay, so maybe we can compare two different methods of why we need scene carving. Here we have some simple method to change the aspect ratio. If this is the original images, then we can crop just the most important part based on this energy map. Okay, so actually we have a lot of image processing methods. Then we can estimate the importance of each pixel. So we can have such energy map or importance map. If the colors are near red or orange, that means the importance is higher than those pixels with blue or green colors. Okay. So if each pixel of this image we can estimate its importance, then maybe we can crop the most important regions and make the width just half of its original. Okay, something like this. So based on this energy map, actually we can crop something here. Okay, so we call this cropping because we just delete the other regions. We just give a rectangle that can include the most important part. And then we just delete the others. So this is a very simple method which is called cropping. Okay, and then based on this importance map, we can also calculate the summation of each columns, and then we can measure the importance by the unit of columns. Okay, for example, these columns, once we calculate the summation of the importance values of one single column, then we have the summation here. If the summation is larger than the other columns, then we can erase the columns with least importance value. Okay, for example, maybe we can erase column here, erase column here. So after we calculate the summation of each column, we can sort the results and delete the column. If we have at least 100, then we can delete 50 columns. Okay, so this leads to the results of C. We have column deletion. So based on these operations, you can see once we can delete the least important columns, but it creates discontinuities of the image content because we have the ladder on the step here. Okay, but once we delete column randomly, or the sorting results of its importance, you can see we create discontinuities of this step. Okay, then we have scene carving we will introduce later. And then we can also choose the pixels. Okay, because we're talking about we calculate the summation of the importance of each row. Actually, we can delete the pixels with blue or green colors. Okay, so you can delete pixel by yourself, and then until the width is just half of your original width. Okay. So by this case, you can see the image content, the structure will be destroyed if we randomly erase the pixels by this image. Okay, so this gives us the motivation for the conventional method or simple method. The result is usually not good. Okay, so that's why we need to apply scene carving. Okay, so let's do the definition of scene. When we talk about scene, actually we create continuous lines from top to bottom or from left to right. Okay, so you can see this line is continuous because it's connected to the neighboring pixels. Okay, so we call this neighboring system in images. Okay, so once we have the image, we have the pixel for each position. So the neighboring system means once we consider this position is P, then we have 8 neighbors around this pixel P. So we have 8 neighbor system. If we consider the neighboring 8 pixels as its neighbors. Of course, we also have 8 neighbor system. Okay, once we only consider top, down, left, and right as its neighbors, then we call this 4 neighbor system. Okay, by scene carving, actually we consider 8 neighbor system. So you can see it goes to the right and bottom corners where we extend this scene. Okay, so have you known the when we erase the scene, how we adjust the aspect ratio? Because you can see if we have the dimension of this image, for example, 100 by 100. Let's see what happens if we remove one scene here. Okay, so you can see this is a scene, right? Okay, and this scene, if it is covered by the pixel here, once we remove this pixel, okay, so if this is 5 by 5, okay, if we remove these pixels and we make the rest pixels just go from the right to left, okay, then we will have the images 4, 5, 5, right? If we remove the pixel here, covered by the scene. Okay, so if we remove one thing, then we make the width of the images from 5 to 4. So maybe you can consider if we can remove the next thing, then this image will go to 3 by 5. Okay, so once we need to adjust the aspect ratio, actually we can remove the scene one by one until it's reached the aspect ratio we want. So that's how this image look like. Because when we need to make the aspect ratio half to the original one, we need to remove a lot of things to make the color number just half of the original one. Okay, so next we will discuss how do we determine which scene we want to remove and how to create such scene. Because we have different ways to draw the scene, right? So how this scene goes like this. Okay, next let's see the algorithm. Okay, firstly we need an energy function. For example, we can calculate the gradient of the images. So we didn't introduce the concept of gradient, but maybe we can assume if we have such an energy map. Okay. So actually we have a lot of different algorithms we can create the energy map here to estimate the importance of each pixel. So given the energy map here, all right, and then we can calculate the energy, and then we can define a vertical scene. Okay, so the vertical scene is defined by Sx. Actually, it's the set of pixels. Okay, so the set of pixels is defined by x of I, and I from 1 to n. Okay, so if we have the original images, we have the resolution. Okay, n by n. Okay, and then what is the vertical scene? We can determine the scene position like this. Okay, actually, you know, the y coordinates of each pixel is just 1, 2, 3, 4 to n, right? And then we only need to determine what is the x coordinates of these pixels along the scene. Okay, so we have the constraint here because we hope the neighbor pixels, the distance will not be far. So x of I minus x of I minus 1, the distance should less than or equal to 1. Okay, so very simple definition for vertical scene. Okay, and then the pixel of the path of the scene S will be IS. Okay, so this is also a set, and I is the image. Okay, so SI defines the XY coordinates. Once we can use these coordinates combined with the images, actually we can derive the intensity of this image. Okay, so next one is to calculate the energy of each scene. Once we can define the scene S, okay, so we can just calculate the summation. The energy of IS, if X is the scene, then we are calculating E of I is I. Okay, so E is the energy map. Okay. So we can calculate the positions of the energy map to see what is the total sum of the energy of the scene. Okay, and then we try to solve this algebra function. So it's optimization equations. So let's see what is optimization equation. Actually, we are trying to minimize this energy function. So if we have defined ES like this, so what is the minimum thing that gives the minimum energy function E of S? Okay, so we can also define E of S is we are using the energy map E, and then we calculate the summation over the first position, the second position to the position of N along the same all positions. And the summation is the minimum. Okay, so we can try to solve this equation. What kind of thing that gives the minimum energy, then that will be our solution. So our optimal solution, we usually use a star to indicate this is our optimal solution. Okay, so next you can consider how to solve this optimization method. Given input image and with the corresponding energy map E, okay, actually you can draw any things if it is follow the definition of a scene. So we have a lot of possibilities. We have a large numbers of different things. So we need to calculate which thing has the minimum accumulation energies. Okay, so how do you solve this problem? How to determine the thing with the minimal energy? Two extra points. If you have your own ways to discover the thing with the minimal energy.有同学有办法吗？好，那我再把这个问题再讲一遍哦。好，假设我们给第一张图，还有它相对应的 energy， 我们现在在这个图上随便画一条线，你都可以把这一条线的 energy 累加在一起，对不对？你就会有一个累加的 energy 的总和了。那你这时候再乱画另外一条线，这时候也会有这条线的累加的 energy 的总和。好，那假设第一条线的总和叫10，第二条线的总和叫12。那我们就知道第一条线的 energy 是小于第二条线的。好，那这时候我们就可以把这条线拿掉了。好，因为它的 energy 是大的。好，但是呢，因为现在这一条线的画法有非常多种。好，这个你要往左弯，往右弯，怎么弯都可以，直的也可以。好，所以实际上当我给你一张这个 energy 的 map 的时候，你要用什么样的做法能够找到最小的 energy 的那一条线？同学有任何方法吗？很笨的也可以，只要能解得出这个问题就好了。好，好。OK， 好，你也太厉害了吧！好，好，那除了动态规划之外，有没有比较直觉、简单的方法是能够解得出来的？比较直觉的方法啦。哦，也许动态规划同学们对那一套不是很熟。好，暴力法要怎么解？好，其实我就是想要听到你用暴力法来解啊。好，那你可不可以帮我来画一下暴力法的话，你怎么用暴力法找到所有的 C？ 你可以来黑板上画一下吗？假设你用暴力法开始画的第一条线、第二条线、第三条线长什么样子，然后最终你可以画出所有的线。
就一点对一点，然后再第二个点，对。
好，那假设这边画完之后呢，接下来画什么？就是你的规则是什么？能够找到所有的 thing。好，没问题，好，这样可以了哈，总成绩加1分，好。好，那我们再请一个同学来帮我们，你有什么样的规则能够画出所有的形？按照同样的规则就可以把所有的形画出来。你拿黑板照画画看。对每个点怎么样？做 BFS， 那你来黑板画画看，我看你的规则是什么？
就是现在是有一张能量的图，
对，
就是你先每一个点，然后应该是往附近能量最小的地方走吧。
但现在是暴力法哦，它没有在管能量，它只是要把所有的线列举出来而已。
直的弯的都算了。
就是我们刚刚讲的 A neighbor system， 只要它是连在一起的都可以这样，但是它只能往邻近的点来走。
那就那不用管能量，就是
对，
直接出去啊。
没错没错。所以规则是什么啊？怎么走啊？你走给我看啊。第一条、第二条、第三条依序要怎么样找，把所有的性找出来。它的规则是什么？
就是好像第一页规则比较好，是这样，然后回来，然后这样，然后这样，然后这样，就是这样，然后回来，然后往这边走，然后再往这边走，再回来。
啊，这个就不行哦，我们只能往下面跟左下还有右下走。
下面跟左下。
下面、左下、右下，只能走这3个点而已。再往旁边的点就太远了，就已经不符合我们 sin 的定义了。好，所以你再讲一次你的规则是什么？假设你走到这个点，你接下来就会有
走到这个点，然后往下或者是往
右下，
然后接下来回去，
对，
回到上一个点，然后先往右下，然后再左下，
对，
然后左下，然后下面右下，然后再回到
对，好，没错，就是这样子哦。好，所以by these rules you can see actually you can enumerate all things within this image, but the number of the thing will be so large. Okay, so next I will introduce another technique, is dynamic programming. Okay, so the first step is to traverse the images from the second row to the last row, and then we can calculate the cumulative minimal energies. Because we are talking about when we traverse the scene from the previous point, then we can go to the button, go to the right button and left button points. Okay, so we can use the current energies and choose the minimal energies from these neighboring 3 candidates. Which one has the smallest energy? Then we can calculate the accumulation results when we travel from IJ to the next point of the scene. Okay, so in this case, we can have cumulative minimum energy map of Mij. Okay, in the end of this process, then the minimum value of the last row indicate that will be the minimum total energies of the vertical sink. Okay, and then in the second step, we backtrack from the minimal entry M to find the path of this optimal sink. So let's see the example here. Once we have the image and we have the corresponding energy map, then we can see how to remove the vertical sink here. Okay, so let me show you this example. Okay, so we have the energy map if we start from the first row here. Okay, so we can see for this position, the energy is 10. And then when the scene goes down and or goes this position, we can choose the minimal energy from these two candidates. So actually we can see this one is smaller, 2 is smaller than 8. So we can have the results goes down here. Okay, so this is the cumulative results. Okay, so we have, if this is M of Ij, okay, for the first row, we have 10, 1, and 5, and 3, and 4. Okay, so when we start from this position and we can go down and right down or left and down. In this case, we only have 2 choices. So the minimal energy is 2. Okay, so the cumulative energy in M matrix here will be 12. Because we are choosing from the minimal energy from these 2 candidates, and this one has the smallest energies. So the accumulation from this position is 12. Okay, and then we can go from this position. Okay, so if we go from this position and we accumulate the energy by 2, 8, and 6, okay, then we can see actually the minimum energy is here. All right, we need to accumulate the minimum energy. Okay. So we need to make sure once we travel to this position, the cumulative energy is the minimum. Okay, so originally the energy is 2, and it can travel from 10 or 1. Okay, so the minimum energy will be 1 to 2. So the energy will be 3. And we can record the paths from 1 to 3. That gives the minimal energies. Next, when we jump to these positions, we have 3 possible candidates from previous step. It goes from here, here, and here. And the minimal cumulative energy is 8 plus 1. Okay, so we have the results 9 here. And we can record how to calculate 9 is from 1. Okay, and then for this position, we also can have 3 different choices. And the label results will be 7, also from 1. Okay, then maybe you can try this example because once this is the last row, then we can accumulate all previous scene energies here until we reach the last row here. Then, for example, this is 10, this is 8. Then we can see this one is the minimal accumulative energies. So we can choose the position here. If we backtrack to its previous position, then we can see how this thing goes from bottom to the last row. Okay, so once we can trace the scene here, then we can remove all corresponding pixels. So this gives us another images. The resolution will be 4 by 5. Okay, so I hope you can try this practice first. So everyone has your A4 paper, right? So we consider this as an exercise, and you will have scores of homework assignment. So please finish this practice, and you can discuss with your classmates. It's okay. So let's see this question. We have the following 5 by 5 images and its corresponding energy map. So you are required to remove one vertical scene to make it 5 by 4 images by scene carving method. Because I've tried this example for you, so maybe we change the question to horizontal scene. Okay. So here, this is not a vertical. Okay, so please try horizontal scene. All right, let's take a break for 15 minutes, and I hope you can take your time to finish this practice. And by the end of class, you need to hang in your A4 paper to TA because it's considered one homework assignment. 还没有好，我今天弄好给你好不好？哦，还是，因为好像我可以自己查，是不是自己查就好？你可以自己查吗？对，因为我刚发现，因为我上次给的好像是 receipt 给的不是 invoice 嘛。哦，是不是？对啊，所以可能不一样。对，如果是这个 invoice，你可以稍微查。因为那个机械性是你希望我说是不是？好，那我等一下。所以就是那个竞赛的部分，他说2组都已经报名进去。对，知道。那如果有同学没有报到的话，那就没办法，就来不及。那就还是要做那个可能真的。presentation 跟竞赛没有关系。对。对啊，所以不管有没有报名竞赛，都要 presentation。所以有没有报名就不影响那个东西的，应该不会影响到成绩之类的。因为那个是主办单位的决定，同学没办法就算。所以那个竞赛是每一组要报名。你说你报名的竞赛，但是决赛那个不要去，是不是？报名没有，意思是说就是我们之前好像听到说，就是经常让同学参加竞赛。对。我觉得意思是说，就是这个竞赛是一定要报，对，一定要报。所以，但是现在只有就成都没有报，只剩下简报。简报组关闭了，不能再报。都没有。对，都没有。那这样子的话，就还没报。那就没办法报，没办法。 Alright, if you know how to apply sync carving to adjust the aspect ratio, then we can actually compare the sync carving to different methods. For example, we can see the figure, what is the average energy for each pixels. Once we reduce the image width up to 20, 40, or 100, okay. So you can see if we apply optimal or pixel, basically it chooses the minimal energy pixels. So you can see the energy, average energy of each pixel actually is the highest. And then for sync carving, you can see actually the energy is very close to pixel or optimal, and is higher than a cropping or color division. Okay, so by the comparison of average energy, then you can see sync carving is a better method compared to color division and cropping. And here we can see different methods how to measure the energies of the map. Actually, we can calculate the gradient. We call that E1. And we also have energy method to calculate the diversity of the energy of each pixel. And then we can also apply histogram of gradient or segmentation method to evaluate the energy of each pixel. Okay, so let's see this example to see the effectiveness of sync carving method. Because we have the original images, where we have a lot of shoes here. After we apply sync carving, could you distinguish which shoes is missing for these three figures compared to the original one? Because if we have a very apparent visual artifacts, then you can discover where the shoes is missing. Because the artifacts is very significant. However, if the algorithm, the result is very good, then it will be difficult to discover where the shoes is erased. Okay, so by comparing these figures, you can see actually we cannot discover the missing shoes within a very short time. That means the sync carving method create very good results. Okay, here we have another example to find the missing person. Once we need to erase the person or adjust the aspect ratio of the images, actually we can erase one person to make the aspect ratio fit our target. Okay, you can also apply these applications to remove ex-girlfriend once you break up, and you may not want to see her in these images. Okay, so by seeing carving, you can permanently remove her in this image. Okay. So here we can see we have different labels of green colors and red colors. That means since we erase the content by the energy, so actually we can use the label. For example, if it is labeled by red, then we give very high energies of these regions. That means once you can see carving, this part will not be removed because you will have very high accumulation results of energy. On the contrary, if you want to remove the girl, then based on these green labels, you can set the energy of these green pixels to be a very small or negative energies. Okay, in this case, all sin will come close to the body of the girl. Then we achieve the goal to remove the girl in this image. Okay, that's all about the method in carving. So, any question about this method? If you have any question, maybe we can explain in Chinese again to help you finish your practice. Okay, if no questions, then we jump to next topic, video connections. Okay, let's see, for analog videos, the color information can be sent in one of three types of analog video transmission format. Okay, so I believe this probably 10 or 15 years ago, we still have analog video recording machines. Then we will use different transmission format such as component, S-video, or composite form. Actually, you can see these video connections a lot in the back of your television. Okay, because even though we have digital TV, we still have such analog video connections in the back of our television. Okay, I'm not sure if you have seen this component video before, because you can see we have three different colors of lines. So that's corresponds to Y and CBCR. Okay, so now you understand the green lines actually is correspond to Y components. So actually it's carrying the brightness information. And then for blue and red lines, it's correspond to CP and CR. Actually, they transmit color informations. Okay, so we call this component videos because we separate YCBCR information by separating lines. Alright, next one is S video. Okay, have you seen this before? No? Okay, so let's see. We have a luminous component and intensity luminous components. So compared to component videos, we have YCBCR. Actually, we have two different lines for luminous component. But for S videos, we only have one lines for luminous component and one lines for luminous components. Okay, and then composite videos, maybe this is more common because we have different lines for videos and audios. Actually, for audios, we have left channels and right channels using red and white lines. And for image content, we use the yellow lines. Okay, so let's see, compositing the signals make it possible to use just one broadcast channels through one physical connections from devices to devices. But the disadvantages is this technology that crosstalk can occur between the color and luminous components because we have luminous and cumulus components within one lines, the yellow lines. Okay, so maybe we have the disadvantages of crosstalk, the information affect each other. So this makes composite videos low qualities of all the other alternatives. Okay, and then we jump to digital transmission format. We have DVI and HDMI. So DVI actually is the abbreviation of digital video interface. And for HDMI, high definition multimedia interface. So you must have seen this before, right? Okay, so let's see, we have three basic DVI formats, DVI-D, DVI-A, and DVI-I for digital to digital connection. So that's what we call DVI-D. D means digital to digital. And we also have digital signal to analog display. So we have DVI-A, that means analog. Actually, you can compare the interface of DVI-D and DVI-A. So if you remember, you can see. Next time, you can distinguish these two types of DVI formats by yourself. All right. The next one is HDMI. This is what we currently use for our laptop. Okay, it's audio-video connections for transmission uncompressed digital data. So we don't have separate lines, for example, yellow, red, and white. Okay, they are all composed together within HDMI transmission format. Okay, and it also applies HDCP, high bandwidth digital content protection, to signals, and it's a protocol for copyright protection. But currently, it's not that common. Okay, then we can go back a little bit to the old times, the videotapes. So for videotapes, you can see it's white tapes. Okay, but actually we are recording video and audios by these tapes in the following format. Actually, we have this region to record audios. And for videos, you can see we have different strips. Okay, so when we rewind these videos, then we can read this line by the sequential order of this tape. Okay, and then for video files, actually we use a lot .avi and .mpeg because usually we apply compression method to the original audio-video files .avi. Okay, so have you used the .mov, QuickTime Movie? Right now? No? How about OGG? No? Real Media, .rm. Okay. Actually, they are very common digital video file. When we have end-to-end transmissions to downloading files, especially when you want to download the videos that boys want to see most every day. Actually, you can open the end-to-end downloading file systems. So you will see a lot of .ogg, .rm files. All right. Next, we will jump to another topic about video compression. Okay. So the first important name is codec. Okay. So codec actually is a composition of two different words, coder and decoder. Because when we apply coder, then we compress videos. When we apply decoders, then we transform the compress the video to its original format. Okay, so could you remember any name we have introduced in our course that is a composition of two different words to a unified one, just like codec? One extra point. We have learned one keyword before. It's also a composition of two keywords. Any idea? Okay, if you don't remember, then let's see the keyword compending. Actually, what is compending? If you remember the process of compending, actually we compress the audio first, and then we expand the audio in the second step. So compending means compression plus expanding. Okay, then we have the keyword compending. So very similar to the keyword codec. Okay, next we will see how video compression is applied by different mechanisms. Especially we have two different compression methods, intra-frame compression and inter-frame compression. So by the name intra or inter, you can see the compression is applied within the keyframe. We call this intra-frame compression. If we consider this is a frame, then intra-frame compression means we consider the spatial relationships within this frame, and then we can compress this frame as a smaller size. So we call this intra-frame compression. And by inter-frame compression, actually we know video is a sequence of images along time interval. Okay, so actually we can compare the redundancy for neighboring frames, and then maybe if we have complete the content of the first frame, then this one is very similar to the second frame. So maybe we can compress the second frame based on the analysis of inter-frame relationships. Okay, so this could be compressed more than the first one. Okay, so you can also consider these two compression methods as spatial compression or temporal compression. Because for intra-frame compression, we only consider the spatial relationships between inside this frame. So that's one method of spatial compression. And for temporal compression, actually we compare the neighboring frames in the time sequence. Okay, so we also call that temporal compression. All right, next let's see more properties of codec. Okay, so the basic method for compression between frames is to detect how objects move from one frame to another. Then we can represent as a vector. Okay, so maybe I can use the same example for you. If we have one pedestrian walking from left to right, so you can see we have very short times for neighboring frames in the video. Okay, so even though the pedestrian is walking from left to right, you can see the moving distance from first frame to second frame. The distance is very short. Okay, So actually, we can estimate the motions, how objects from one frame to another. For example, if we have the bounding box of the first pedestrian, and then we have the bounding box for the pedestrian in the second frame, then we can distinguish what we call motion vectors. What is the motion vectors? To move the head in first frame, then it goes to the second frame. What is the motion? For example, the center of the head, for example, is 1, 1. Then in the second frame, the center of the head becomes 3, 1. Okay, then we know the motion is along x-axis, and we can estimate the motion estimation. Once we can estimate the motion vectors, then you can see the basic compression concept is to replace the rectangle to the rectangle in the second frame directly. Because we know this person is moving from previous frame, and we know its previous positions. So this achieves the goal of compression. Once we can, for example, pass the rectangle directly here, then we don't have to record anything of this region. Okay, we can, based on the motion vectors, to see the pedestrian, its location in the previous frame, and we can use the content directly in the previous frame. So this achieves the goal of compression. Okay, so motion estimation is very important for video compression because we can use the content appear in the previous frames. So next, you will see a lot of algorithms how to apply different motion estimation algorithms to determine where the objects in the previous frame. All right. Next, let's see. For the codec, it allows you to select either constant or variable bitrate encoding. Okay, so maybe you can relate this concept to what we have learned before, because for Huffman encoding, we assign different bit or different bit rate for different patterns, right? So for videos, you can assign constant bit rate, or you can also assign variable bit rate. So we have different terms for this mechanism, CBR or VBR. So if we don't consider the content, how complicated or how simple it is, then we can apply constant bit rate, CBR. If we want to apply more bit to complicated regions and assign this bit to smooth or homogeneous regions, then we can use VBR, variable bit rate encoding. Okay, and next keyword is asymmetrical codec. That means usually we pay a lot of attention and we put a lot of efforts for encoding part. So the algorithms are usually very complicated, very computational, high computational complexity. But for decoding part, it's relatively easy and fast. So we call this structure a symmetrical structure. All right, next let's see quickly through the history of MPEG compression. Because previously we have two different groups to provide the standard of video compression. So these two groups will be MPEG groups, and the others we have H.264. Okay, so let's see these two standards. The first pass, you must be more familiar with MPEG series because we have MPEG-3, and back to the compression of videos, we have MPEG-2. Actually, I'm not sure if you have known the history of MPEG, because after MPEG-3, we have MPEG-4, MPEG-7, MPEG-21. Okay, so it's through a long, maybe 1 or 2 decades for this MPEG series. And then for another series, we have H dot something. Okay, for example, 2061 or 2063 or 2064. Okay, and then for some year, these two standards merge to one standard. So we call that joint ITU-T and MPEG standards. Because at this year, H.264 is merged with MPEG 4 Part 10. So actually, we have no parallel standards. At that year, we have a unified standards for video compression. Okay, so let's see the goal of video compression. So the target for video compression is to double the coding efficiency compared to any existing video coding standards. Okay, so what is video coding efficiency? That means we can use less bit to represent the same video content. So let's see, the y-axis here is S megabit per second. If we have a video, then we know for video, 1 second we have 30 frames. So how many megabit we use for the content within 1 second? So we can use this as an indicator to see the coding efficiency of different coding standards. So let's see this figure. If we have an MPEG-2 here, then we also have another series of H dot something. We can see it here. Okay, so you can see previously the coding efficiency H series is better than MPEG because we can compare within 1 year the mbits or the bit rate. The H series is smaller than MPEG series. Okay. And then we mentioned that for some years, these two standards merged to another standard. So we can see a very clear gap that the coding efficiency is improved significantly at that year. Maybe we can see this quantitative comparison, how these two standards and show its average bit rate. Okay, so average bit rate saving are related to another codec. Okay, so let's see for H.264, when it compared to MPEG-4, then the bit rate saving is 37.44%. Okay, so you can see the saving is more significant when it compared to the previous standard H.263 or MPEG-2. Okay, next let's see the definition of bit rate. It often refers to the number of bits used per unit of playback time. So the unit of playback time, usually we use 1 second. So within 1 second, the number of bits is what we call bit rate. Okay, so the encoding bit rate of multimedia file is the size of the multimedia file in byte divided by playback time. So actually, you can use the file size divided by the playback time to calculate the bit rate. For example, if you have a video file that is 200 megabytes and the time duration is 30 minutes, okay, then actually you can use the file size divided by the playback time to calculate the bit rate. Okay, next let's see the definition of peak signal to noise ratio. Actually, we have introduced this in our first homework assignment because once we have compressed the frames of videos, we need to calculate what is the distortion. So we can use the maximum numbers compared to the mean square error. Okay. And by this ratio, we use 10 times 10 to calculate what we call PSNR. Okay, so let me ask you one question. By the definition of PSNR, if we expect a better quality videos, the PSNR should be larger or smaller to indicate better qualities. The value should be goes higher and higher, then it will be a better quality video, or the value should be lower and lower. Which one? Lower. Okay, so how do you consider this equation? If this PSNR has lower values, then it indicates the quality is better.好，那我们看一下这个公式啊。我们如果用 ij 减掉 kij， 其实这个就是我们刚刚讲的压缩过后的 video 跟压缩前的 video， 它的画质差了多少？所以我们如果用同一个位置的 ij 去计算它的影片整体的差异，那这个差异的总和就会是我们所谓的 mean square error。也就是说，原本有一张没有压缩过的画面，接下来你把它压缩了。如果压缩完之后，这个画面全部都烂掉了，它跟原本长得很不一样，那代表它的 error 是很大的。假设压缩完之后，它的值跟原本一模一样，这个值就会是0。好，那这个值的大小，因为这个是平均嘛，好，这个 error 的总和的平均，它的最大值是多少？其实就是255嘛。好，因为你这个值最大跟最小差异的范围，假设你原本是0，最后变成255，那这个减起来的 difference 或是 square error， 好，就会是255的平方。那假设你是100变120，这个值就会比25还更小，所以最大的 difference 就是255的平方。好，那接下来我们演算出这整个画面的一个 pixel 的平方的平均，好，那就代表所有值的平方结果的总和，好，这个 average 大概长什么样子？所以我们就用最大可能差异除以现在这两个画面的差异，来看看它的差异量的对比到底有多少。好，所以你的结论是怎么样？怎么看呢？好，有同学知道这个结论是什么吗？好。对，但我们刚刚问题是 PSNR 会大还是小？好，品质越好 ，PSNR 会越大。好，那我们看一下为什么。好，我们所谓的品质越好是什么？这两个相减的值很小，甚至完全没有差异。好，那所以呢，你在这边除的时候，这个 max 是一个定值嘛，这个定值就是255的平方，所以这边是不会变的。那你每一次就是单用这个值来计算。那当这个值很小的时候，一个定值除一个很小的值，好，这个值就会大。那你这个定值除一个很大的值，这个值就会变小。好，所以 PSNR 这个指标呢，就是这个值越大，代表影像品质越好。 Okay. Okay, so based on the definition of PSNR, then we can use these two indicators, B rate and qualities, to indicate the performance of different codec. Because actually, we know if we use this bit, then the B rate will be more efficient. But if you use this bit, then it means maybe the content of the video will be degraded. Okay, so it's just a trade-off between these two indicators. If you want to preserve better qualities, intuitively, if you assign more bits, then the quality will be better. But we want to achieve higher coding efficiency. We want the bitrate to be as small as possible. But once the bitrate is too small, then it can damage the quality of the videos. Okay, so we need a balance between these two indicators. So next, let's see how to compare these four standards using this figure. This figure is very famous. We call that RD curve, rate distortion curve. Rate means B rate. Distortion means the quality PSNR. Because if PSNR is very high, then that means no distortion. If PSNR is so low, then the distortion is very significant. Okay. So next, let's see how to compare these three curves to see which standard is better. Okay, the first thing is you can draw a vertical line here to compare by the same B rate, which quality is better. Okay, so if we draw one line here, you can see for H264, the PSNR is 34, but for MN2, the PSNR is only 30.5 something. Okay, so given the same B rate, you can see the performance of H.264 is better than MN2. And in addition, you can also draw a horizontal line here. Okay, by the same PSNR, then which one use less B rate? Okay, if we consider 33 here, then you can see for H.264, the B rate is about 48, but for MPEG-2, the B rate is 40. Okay, so compare the same B rate or the same PSNR, we can see actually H.264 is better than the other standards. So actually, you can jump to the conclusion if the curve is above the others, then the highest one is the better one. Okay, next let's see video compression. Actually, this is a very large system. It includes encoding and decoding part. And then it also includes the network abstraction layer because we have different physical transmission protocols, how to transmit by networks. So we need extra layers to to have another interface between coding layers and transmission layers. Okay, so you can see the application is wide because it can be used for broadcast and streaming, and maybe we can produce ISO media file format, and then for mobile communications, we also need to communicate by different videos in these applications. Okay, next let's see the data structure of video compression. So actually, this data structure, I consider it as a very fine art, okay, because it's so delicate and the design is so smart, okay. So I hope you can remember this data structure because you will never see more complicated data structure like this. Okay, so let's start this demonstration from sequence. We know the video is a sequence of images. Okay, so the next layer of data structure is group of pictures. Okay, so if we know we have the original video as a sequence of images, actually we can group these pictures by different GOP. Okay, for example, the first frame to 10 frames, it will be the first group. And frame 11 to frame 20 will be the second group. Okay, so that's the group of pictures. Okay, and then for each pictures, we can also have different structures, such as slides. So if you remember our previous definition, upper field and bottom field, actually we are partitioned two different regions within one frame. Actually, for the single pictures, we can partition these frames as different slides. Okay, so we will see the definition of slides later. Okay, so for different slides, we also partition the slides into different micro blocks. Okay, so if you consider micro block is 16 by 16 pages or 22 by 22 pages, then it could be the unit of different micro blocks. And for micro blocks, it's also composed by different rulers and rulers component, Y, C, D, C, R. Okay, so you can see this data structure, the top is the sequence, the bottom is the component of YCDCR within each pixel. For each pixel, it can be divided into three components, YCDCR. So you can see we need more layers between the sequence and between the unit YCDCR. Okay, next we will see more details about these structures. Because for video compression, it's very complicated. We can apply the concept of compression for each layer of this data structure. Okay, so this is the video coding layers we have mentioned. Upper layer or bottom layer. Okay, we can also call it top field or bottom field. Okay, so next, let's see the terms adaptive frame field coding operation. So we have three different modes we can choose. Then we adaptively choose different modes for each frames in the sequence. We can choose either frame mode. So we process the video compression by all frames. So we call that frame mode. We can also apply video compression by field mode. The compression is within upper field or bottom field. Or we can also mix these two modes together. Then we have frame mode and field coding. Okay, so you can see when we can choose different mode adaptively based on the content of videos, then we can achieve higher bitrate saving, 16% to 20% saving over frame only video compression. Okay, so when you study the codec of H.264, you may see this method MBAFF micro block adaptive frame field. Okay, so actually we are choosing different mode from frame mode and field mode to process different micro blocks. Let's see the definition of slice. Okay, a picture is split to one or several slices. So you can consider what is a slice? It's just a sequence of micro block. It's the minimal self-decodable unit. So if we consider this is a key frame, okay, so you can see actually it's 9 by 12. 9 by 9. Okay, so if we consider a series micro blocks, so maybe this is the first part of the slice number 0. And then from this position, we can go back to form the slice number 1 and slice number 2. Okay, so you can consider if we have different partitions within the images, then we can create different slices. Okay, and for microblocks, it contains 16 by 16 rootless and coreless component. Actually, it's just 16 by 16 patches. Okay, that one we define as microblocks. Okay, so if we can partition the images to the basic unit of microblocks, then the microblocks can form different slices. For example, we have microblock 0, 1, 2, 3, 4. If the last one is 20, then microblock 0 to 20 will be slice number 0. Okay, so this is how we partition the images to different layer of data structure. Okay, so if you remember how we transform from RGB model to YCBCR, we can just apply this simple multiplications and additions. Then we can transform RGB to YCBCR. So next is the chrominance subsampling. I believe we have introduced this before, right? In Unit 2 or 3. Have we introduced this before? 大家都忘记了吗？这个有讲过吗？有讲过，好 ，OK， 好，那我们就直接跳过啊。Okay, so once we know how we apply chrominance subsampling, then we can combine chrominance subsampling with top field and bottom field. Okay, so for example, this is the allocation of 4 to 2 to 0. Okay, and then we can combine 4 to 2 to 0 with top and bottom field. Then we can separate our bottom field and top field by different chrominance subsampling. All right, next one is called flexible microblock ordering, FMO. Okay, so our slice group contains multiple microblocks. So the pattern of microblocks defined by a microblock allocation map is called the order of microblocks. And slice group may contain 1 to several slices. Okay, so what is FMO? Let's see. Previously, we have the order of microblock within the slice, for example, 0, 1, 2, 3, 4, 5. So this is fixed order of microblocks, not flexible ordering. However, for the MPEG-4 or HRF264, we can define more flexible ordering of microblocks. For example, we can define this region as slice group 0, and this is slice group 1, and we have something like the background is defined as a slice group 2. Okay, so you can see actually the microblock ordering within slice group 0 it's not start from 0. Maybe this position is already 13, 14 or something. But 13 is within slice group 0, and 0 within slice group 2. Okay, so this is what we call flexible microblock ordering. We don't have to follow the very strict ordering 0, 1, 2, and 0, and 9, 10, 11 in slice 1. Okay. Alright, next mechanism is called arbitrary slice ordering. Because we have mentioned slice is the minimal self-decodable unit. Okay, so when we transmit the data, we need to use the minimal unit of slice. You cannot transmit microblock as a unit. Okay, so what is arbitrary slicing order? Because when we transmit slice to online via the network, for example, we have slice 1, 2, 3. But during the receiver, we have different network conditions. So maybe we have different order. For example, the first received slice is slice 2, and then we receive slice 0 and slice 1. Okay. So in this case, the decoding of slice is independently decoded slice. So it's not depends on the order of slice 1, 2, 3. Okay. So we can receive slice 2, and then we can decode slice 2 first, and then we receive slice 1, and then we decode slice 1. Okay. So you can see the mechanism is very flexible. Even we have different network jamming or different network conditions, we still can decode different number of slices. All right. Next, let's define different keyframes. Okay. So each picture can be decoded using different coding types. We have 3 different types: I frame, P frame, and B frame. Okay. So I frame means we apply intra-prediction for these frames. So let's consider this is a sequence of images. So this is what we call a video. And then we give different names for the frames. For iframes, that means when we apply video compression, we only consider intra-prediction. We consider the spatial relationships within these frames, and we apply the video compression method. We didn't consider the other frames. So this is iframe. Okay, for P frame, that means we apply interpretation. So when we apply compression method for these P frames, actually it refers to the previous I frames. Okay. So for interframe video compression, we call that P frame. Okay, the last one, B frame. Actually, we can use bi-directional motion compensation prediction. So for B frames, it can refer to the previous I frame. It can also refer to the later P frames. Okay, so both directions, the information can be used for B frame for video compression. So by the name of the frames, you can see actually it's related to its video compression method. Intra-prediction, interpolation, or bi-directional compression. Okay, next, because we have only 15 minutes left, so let me jump to the motion estimation algorithm directly. Okay, so we call this block matching algorithm. Just like I said, if we know, here we have a vehicle here. So if we know the vehicle in the previous frame and the position is here, then we can record the motion vector directly. And then based on the motion vector, we can see once we need to recover the region here, and we have the motion vector tells us where the vehicle in the previous frame. Then we can use the position plus or minus the motion vector to discover the original position of the car. Then we can use the position here to replace the content here. In this case, we don't have to compress the original video content here. Instead, we only need to compress the video motion vectors and the residuals, the difference between two regions. Okay, so here we need different block matching algorithms because we want to match. If we have a block contains the tire of the vehicles, we need to discover where is the tire. So we need to compare the block by this block to previous block one by one. If we can have the minimal mean square error, then we can discover maybe the tire is here. Okay, so this is what we call block matching algorithm. Actually, we are trying to discover the motion vectors from one local block. By the motion vectors, we can discover where it is in the previous frame. Okay, so the block matching algorithm is very easy because once we can calculate the difference of the position x, y to different candidate position x plus s, y plus t, and we can calculate the difference mean square error mean estimate values, then we can discover what is the most similar block in the previous frame. Okay, so let's see the most stupid method, full search. Okay, so by full search, we don't have any techniques. We just compare all possible blocks, but we still have smarter ways for all comparisons because we know the time in interval between two frames is very short. So we don't have to search the whole frames in the previous frame. We can define a certain range because within a very short time of the neighboring frames, the motion vectors will not that large. Okay, so we can define a reasonable search range here. Then we search all possible microblocks and compare the difference. Okay, so the exhaustive search will be like this. Once we have the microblock in the current frames, then we have the same positions in the previous reference frames. And then we can define a search range here. Okay, after that, we compare the microblock by the first microblock in the search range. For example, we can start from the left top corners. This is the first microblock. And then we can calculate the mean square error of this one and this one. Then we can have the results of the difference. And then we can move to next candidate. For example, this one and this one by the zigzag scale order within the search range until we calculate the results for the last microblock. Okay, so between all these results, we can discover which microblock is the minimal. Okay, and then we can calculate the motion vectors because for these microblocks, we have its coordinates. And we also have the current blocks. We also have its coordinates. So if we minus the coordinates, then we can get the motion vector. Okay, so this is the exhaustive search. So no tricks, just compare all possible microblocks one by one and get the minimal microblocks. All right, next, let's see fast block matching algorithms. Okay, because for exhaustive search, actually, if we apply such searching method for each micro block, the total computational cost will be very high. Okay, so we have different fast algorithms. The first thing you need to notice is it's not that accurate as exhaustive search, but it can save a lot of computational time. Okay, let's see two famous fast algorithms, 2D localism search method and 3-step search. maybe we can see the example directly. Okay, for 2D logarithm search, actually we only consider the current microblock positions and 4 candidate positions. Okay, so if this one is the previous frame, so remember we have the current frame and we have our current microblock. So we can start from exactly the same position and 2 positions nearby. Okay, and then we can calculate the mean square error of these 5 candidate positions to see the difference of microblocks. Once we have the smallest one, then we mark as the pink positions. So this gives us the smallest mean square error among these 5 candidates. Then we can jump from the original position to the new position here. Okay, and then we apply the same 2D logarithm search algorithm. We have these 4 candidates around. Okay, and then by the previous iteration, I will just calculate these 5 results and choose the minimum one. So in this case, this one and this one is already calculated in the previous iteration. So next, we only need to calculate the position here, here, and here. And then we can compare where is the minimum mean square error among these 4 peak regions. Okay, and then we can choose the minimum one if we indicate by the red position. Okay, then we can apply the algorithm again. So we have 2, 3, 3. Okay, then we can choose the minimum 3. Then we apply the algorithm again. Okay, so in this case, we have reached the edge of these search areas or boundary of these search areas. So we shrinkage the search area by 1 step. Okay, so for the neighboring pixels of this position, we have this 1, 2, 3, 4, 5 positions. Okay, then we choose the minimum mean square error from these 5 candidates. In this case, we have the minimum value by the gray position. Okay, in the end, this is our final target. We assume by this fast algorithm, this is the smallest one among all search regions. So we can record the function factors from this position to this position. Okay, so this is 2D logarithm search method. Next, let's see another famous algorithm, which is 3-step search method. Okay, let's see this example directly. Okay, so once we have the corresponding positions from the current microblock to the previous frame, so we know the position is here, and we define the search range here. And then we define 8 different neighbor positions, which is 1, 2, 3, 4, 4 pixels away. Okay. So in this case, we can calculate the mean square error by these 9 positions compared to the current block in the current frame. Okay, and then we can choose the smallest one. Once we choose the pink positions, next we just shrinkage the distance of the neighboring pixels by half. Okay, so in this case, we just consider pixels 2 pixels away. So we have these 8 neighbors. Okay, once we have these 8 neighbors, we can also consider the position with the smallest values. Maybe it's the position of orange. Then we can shrinkage the distance by 1. Okay. So we search the neighboring positions marked by 3, and choose the smallest one among all possible candidates. Then results will be marked up by gray pixels. So in the end, we call this three-step search because after that, the algorithm terminates. The first step, we have 4 pixel away neighbors, and then 2 pixel away neighbors, then 1 pixel away neighbors. After that, the algorithm terminates. Then we just determine this micro block, we have the smallest mean square error compared to our current micro block. And then we can record the motion vector. All right. Next, let's see another advanced block matching algorithm, which is called downhill simplex search. Okay. So actually, previous algorithm we have fixed step for 3-step algorithm, but for downhill simplex search, we have 4 different stages, and we can switch between these 4 stages. Okay. So once we have the calculation of mean square errors of the first step, then we can discover 3 locations that are surrounding by the centers. Okay. And then we can calculate the average positions of these 3 positions. We call that P average. And then for reflection, that means we need to search for the directions which is opposite to pH. pH means the highest mean square error. That means if we go that directions, we reach to very, very high mean square error. So this means we should go to the opposite directions. So we call this reflection. So we jump to another position, another directions, PR. Okay. For stage 2, we have extension. If we can check PR is a better directions, then we can go further. So this calls extension. We have this mathematical equation to determine where is the next location. Once this direction is correct, then we can go further. So we apply extension. And then we have contraction. Once the other direction is not good, then we can go back to our previous directions. So we call this contraction. So the contraction actually is the interpolation of pH and P average. Then we can go something between the middle. Okay. So the last stage is shrinkage. Okay. Once we reach to the boundary or the triangle is very, very small, then we can calculate the shrinkage results. Actually, it's just the middle points of pH to PL and PN to PL. So actually, this is the lowest SAD PL. This is the highest SAD PH. And this is something in the middle. Okay. Then we can shrinkage the triangle to a smaller search regions, which we call shrinkage. Okay. So actually, we are not considering multiple locations or multiple candidates. Actually, we can choose different steps to see if we choose better candidates. If this is better, then we can reflect or extension. If the candidate is worse, then we can go back to contraction or shrinkage. Then we can jump between these 4 stages to find the final results until the triangle is shrinkage to 1 pixel distance triangle. Then the algorithm terminates. 好，那我们终于在4点前把这个演算法讲完了。好，那我们那个之后的期末考呢，就这个单元就是我们有上课讲过的地方，我们才会纳入期末考的范围。好，如果上课没有讲的地方，期末考就不会考，好不好？好， 那大家需不需要一些练习啊？这个演算法，我们可以给同学一个实际的例子，让同学来练习一下这个 block matching 的演算法。大家要这个 homework assignment 来做一下练习吗？还是你们觉得自己可以不需要这个练习？好，不要练习的举手，我看看好了。好，很勇敢啊，哈，这个有3种。那要练习的举手，我看看。好，那我们还是不要好了，好。那就同学自求多福咯，哈。如果你们期末考看到这个演算法的题目，你们要自己会算，到底哪一个是最佳的 block matching 的结果。好，那看看今天上课的内容，大家有没有什么问题？好，没有问题的话呢，就请大家好好准备我们下礼拜的 final project 的展示，好，看同学们这学期做的怎么样。好，那我们就到这边下课。